artificial intelligence. You hear that term everywhere, right? But how does it actually work? Well, you might be surprised to learn that the whole journey to create a thinking machine wasn't some single magic breakthrough. Instead, it was a long series of brilliant and sometimes totally flawed ideas. So, let's dive into that journey, the quest to build an intelligent machine from the ground up.
You know, it all really boils down to this one huge question. Can a machine think? And this isn't just some techie problem. It's a deep, philosophical one that makes us ask, well, what does it even mean to be intelligent in the first place? This question is the spark that lit the fire for the entire field of AI, and it's fueled over 75 years of innovation. And honestly, we're still kind of searching for the answer. So the guy who basically dragged this question out of the philosophy department and into the lab was the absolute genius Alan Turing. See, back in 1950, he didn't just sit around and wonder about it. He came up with a concrete, practical way to actually test for an answer. He turned an abstract debate into a real scientific challenge.
Okay, so how do you even start to test if a machine is thinking? Turing realized that before you can build an intelligent machine, you gotta figure out what you're even looking for. Like, what does intelligent behavior actually look like? His solution was this incredibly clever experiment he called the imitation game.
Okay, so check out this setup. It's so elegant. In phase 1, you've got a human interrogator asking questions to a man and a woman in different rooms. The goal? Figure out which one is the woman. Now, the man's job is to trick the interrogator. Then, in phase 2, you swap out the man for a computer, but its goal is exactly the same. Fool the interrogator. And this is the brilliant part. If the machine is just as good at fooling the human as the man was, Turing said, then it's demonstrating intelligent behavior. It's not about consciousness or feelings. It's all about performance.
All right, so with the test in place, the race was on to actually build something that could pass it. And the first big attempt to create AI didn't involve any kind of learning or creativity. Nope. The strategy was to take all of human expertise and try to translate it into a massive, rigid rulebook of pure logic.
Yeah, in this timeline, it's just a perfect snapshot of the roller coaster that was early AI. It kicked off with this huge explosion of optimism. I mean, people genuinely believed human-level AI was maybe a decade away. But they pretty quickly slammed headfirst into the messy reality of common sense. You know, all those unwritten rules we live by. And they realized just how unbelievably hard this problem really was.
But you know, out of all that frustration came a really big idea, the expert system. The thinking was, let's stop trying to build an all-purpose general intelligence. Let's just focus on one super narrow area. You find a human expert, say a doctor or a mechanic, figure out all their rules of thumb, and then you painstakingly program those rules into a machine.
And what's so cool about this slide is you can see just how beautifully simple and totally rigid this logic is. This is from a real system, by the way. Step 1, it gathers a fact. The environment is machines. Okay, step 2, it applies a rule. If the job is repairing, then the response is hands-on. And boom, step 3. From just those two little pieces, it reaches its conclusion. It's a perfectly clear, traceable, and completely uncreative line of reasoning.
But this whole approach, it just slammed into a giant brick wall. I mean, think about how a master chef cooks or how a doctor diagnoses a rare disease. So much of what they do is pure intuition. It's a gut feeling. It's built on years of subtle experience. How on earth do you write that down in a rigid if-then statement? The short answer is you can't. And this problem became famously known as the knowledge acquisition bottleneck. So that bottleneck, it forced everyone to take a huge step back and ask a really radical question. What if? What if instead of programming intelligence one painful rule at a time, we could build a machine that just learns on its own, kind of like how a human brain does?
And this table just lays it all out so clearly. You've got your conventional programs over on the right. They need perfect, exact data to work. Then you have expert systems, which are a bit more flexible, but still really rigid. But what researchers were really after was this column, all the way on the left, the human expert, who can work with fuzzy, incomplete info using intuition. That was the new goal.
And that quest led them to dust off an old idea, the artificial neural network. This was a total game changer. Unlike an expert system, you don't give a neural net any rules. You don't program it. Instead, you just show it tons and tons of examples, thousands, millions of pictures or sounds or text, and it figures out the patterns all on its own. It literally teaches itself.
Okay, so learning from data was huge, but it wasn't the whole story. there was another fundamental problem with how computers think. The real world isn't black and white, right? It's filled with shades of gray. But traditional computer logic is built on a super strict foundation of true or false, 1 or 0. It's just not built to handle all that ambiguity.
I mean, just look at a sentence like this. To you or me, it makes perfect sense. But to a traditional computer, it's basically nonsense. What in the world is slightly overloaded? How long exactly is a while? Without precise numbers, the whole system just breaks down. This is where a totally different kind of logic had to come into play. And that's where fuzzy logic comes in. The core idea here is to move beyond that simple true or false world and allow for degrees of truth. It's basically a mathematical way for computers to understand that something can be, kind of true. It lets a system reason with vague words like slightly, hot, or fast, just like we do.
And here's a super simple way to see how it works. Fuzzy logic gives you a framework for mapping these vague human words to precise numerical values that a computer can actually process. So, often might get a value of 78 on a scale of 0 to 100, while sometimes becomes a 20. It's like a translator, building a bridge between human language and machine logic.
Okay, so let's tie all of this together. We've gone from these rigid, rule-based systems to brain-inspired networks, and finally, to a type of logic that can actually handle ambiguity. The big takeaway here is that these aren't rival ideas fighting each other. They're all just different tools that, together, make up the powerful AI toolkit we have today.
And you'd use each tool for a different kind of job, right? A rule-based system is perfect for something with clear expertise, like a diagnostic checklist for a machine. A neural network is what you'd use to find hidden patterns in millions of credit card transactions. And fuzzy logic? That's great for controlling something like a washing machine, based on how dirty the clothes are. But the real magic happens when you combine them in hybrid systems.
And that brings us full circle, right back to where we started. We began with Turing's simple question, can a machine think? And now we've built systems that can learn on their own, that can reason with ambiguity, that can make incredibly complex decisions. So the question isn't just for scientists in a lab anymore, it's for all of us. As these AI systems get more and more powerful, how is that going to change our very definition of what it means to be intelligent?